It came out the last one.
I can't believe he took them.
Does anybody have any questions before we start?
Yeah. Unless he actually does it.
When is the lab report?
Pardon?
Lab report, when is it?
Have you given any directions yet?
I was just gonna go with the BBFD next slide.
Okay, that sounds reasonable. I didn't want to say anything that was contrary to what we gave you. So we'll try to make the beginning of this laboratory period, unless the lobby has given any different directions. Okay. Any other questions? Okay. Today I'd like to spend most of the period talking about design space exploration. We talked about design spaces last time. We looked at the first operational amplifier structure, which was a single-ended input, single-ended output structure. And we saw that we could apply feedback, much like you did to the op-amp circuits in 230. And this is possible when you don't need both inputs on the op-amp. Most of your op-amp applications don't need both inputs. You ground one input, so you don't need two inputs. We modeled the amplifier structure as a two-port network with two conductors, two transconductance elements, one G and one GM. And we can model any single-stage op-amp with an infinite impedance this way. The only difference between one structure and another is the value for big G and big GM. We observed that the gain bandwidth product and the DC gain are two of the most important parameters of an operational amplifier. And we have a whole bunch of others we're interested in, but usually those are the ones that we're most concerned about. We looked at the design space, and we saw that to design this circuit, we needed to control or determine what the dimensions were of the device, the quiescent input, and the quiescent drain current. So there were four design variables we had to work with. However, we knew that there was a relationship between the drain current, the quiescent input, and the W and L. So that means that there were really only three design variables left, but W and L always appear as a ratio. So that means there's really only two design variables left. And if we have constraints for a gain bandwidth product and a gain, we've got a completely constrained system. The design space that we were looking at then, which we called the natural design space, was comprised of two parameters, W over L and IDQ. But then we looked at an alternate parameter domain, and that alternate parameter domain was the power and the excess bias. And we saw a big difference between the gain and the gain bandwidth product requirements in terms of the natural parameter domain and the alternate parameter domain. What was the big difference here?
The alternate, you could change the gain bandwidth and keep the gain like the same, so they wouldn't be influenced with one another. And then the natural one, they both change since both of the variables.
That was a really important characteristic. So we don't have complete independence, but we have sequential design or tuning capabilities. So as was pointed out, we can set the gain by adjusting VEB, and once that's determined, we can let the power determine the gain bandwidth product. That's a really useful property for characterizing things this way. So let's go and move backwards now. If we do the design in the alternate parameter domain instead of the natural parameter domain, we've got to eventually get back to the natural design parameters because that's what we put in our circuit. And if there's too much work to get back, then working in the alternate parameter domain may not make a lot of sense. So after we've determined P and VEB, I haven't even given a thought to area. I haven't even given any thought to W&L. I haven't given any thought to IDQ. I've only been concerned about the power and the excess bias is. But I've got to go back eventually and get W&L, IDQ, and VNQ because I need those to complete the design. So I know that power, if VSS equals 0, is equal to IDQ times VDD. So I just have to divide the power by VDD, and I've got IDQ. That was one of the design variables I needed. And I know that it should have been VD minus VSS here if VSS is not 0. And I know that the drain current, which is also IDQ, is equal to mu Cox W over 2L times VGS minus VT squared, which is the excess bias squared. But IDQ is equal to what? IDQ times VDD minus VSS is equal to power. So I can substitute from IDQ in this expression here, P over VDD minus VSS, and I get the expression that says that P over VDD minus VSS is equal to mu Cox W over 2L times the excess bias squared. And I can solve this equation for W&L now. That's why I've got W over L. And I know the relationship between the requested input current and the device dimensions. So this could be V and Q. So the bottom line is it's real easy to move back to the natural parameter domain if I do the design in the alternate parameter domain. Yes?
Where does the factor of 1/2 go from when you were solving on the board to when it's actually solved?
It's how do I want to say it? Some people never make mistakes. I have a president that never makes a mistake. You got an instructor that makes a mistake once in a while. So it goes into that mistake pool.
Sure.
Thanks for pointing it out. I will correct it. I'm missing a factor of 2 in this equation right here. So let's go back and look at the same problem now and ask the question, what if the design requirement was that V and Q equals 0? That's convenient to make V and Q equal 0, isn't it? Before, once we had our design done, we solved for what V and Q was. V and Q might become out minus 1 volt, might become out plus 1.5. That might not be what you want. You might prefer to have V and Q equal 0. What if V and Q is equal to 0? Well, we can increase the number of constraints that we have from 1 to 2. One constraint we started out with was the relationship between V and Q and the W&L and the IDQ. I can add 2 constraints. I can also require that V and Q equals 0. But if I do that, I'm going to have to decrease the number of degrees of freedom I have in my design by 1. So I probably won't be able to meet both the gain and the gain bandwidth product requirements because I used my 2 degrees of freedom up previously to to set the gain and the gain bandwidth product. If I fix E and Q, I can't have two more constraints. So that means that I can either have a gain constraint eventually or a gain bandwidth product constraint, but not both. So the question is, how can one meet two or more performance requirements with one design degree of freedom with the circuit? And either you're lucky and it just happens that you met both design requirements, or you can't do it. If you can't do it, what do you do? Look for a different circuit. Remember, that's the characteristics of this circuit. It's not characteristics of all circuits. Let's talk a little bit about exploring the design space. When we look at this two-dimensional design space, power and the excess bias, we can look at the characteristics that this op-amp has, the gain and the gain bandwidth product, throughout that design space. So let's ask the question, how does the gain bandwidth product of a single stage amplifier change with bias current? I made a statement last time that the gain bandwidth product depended linearly on power. Remember that statement? But I had a couple other qualifiers before I made the statement. So I can't come in today and say the gain bandwidth product, well, I can say it, but I wouldn't be truthful. If I come in and say gain bandwidth product varies linearly with power, is that a true statement? Well, I made that statement last time only after I had a couple other qualifiers. In general, it's not a true statement. So how does GB, a single stage amplifier, change with bias current? Well, GB is equal to GM over CL, and GM is 2IDQ over V excess bias. So how does GB vary with bias current? Linearly. It appears that GB increases linearly with IDQ. Okay. Here's that relationship. I can also write GM in this form. The square root of 2 mu C ox W over L times the square root of IDQ. And now I ask the same question. How does GB vary with bias current? What? Square root. Varies with the square root of the bias current. Oh, we haven't changed circuit structures. But we've got two different answers to the same question. Is there anything wrong with having two different answers to the same question? What? I think that's a concern, isn't it? So if you plot GB versus IDQ, it suggests this is happening. I can also write GB this way. And now ask the question, how does GB change with bias current? Doesn't. There's no bias current in that expression. So GB is independent of IDQ. I can write it this way. And now I can say that GB decreases with the reciprocal of the square root of the bias current. And I can write it this way. And now GB decreases linearly with the bias current instead of the square root of the bias current. I haven't made any mistakes. But I appear to be having different conclusions. So Can somebody help resolve this, what appears to be a paradox here? But by the way, I should point out, it's not uncommon to see an author in a textbook or an author of a paper make statements like this. Yes?
Doesn't power have IDQ in it? Isn't it made up of that? IDQ times EDD?
I guess power is a function, but there's no power in these two expressions.
But there's a few of the other ones.
Yeah.
So does it just depend on which variables you want to change?
That's right. So what happens here is I assume that Vx's bias was constant. And here, I assume that WRL was constant. And here, I assume that P and Vx's bias were constant. And here, I assume that WRL was constant. So I made different assumptions. I can do that. I'm in a two-dimensional design space. And I'm only looked at the effects of one parameter. So how that one parameter affects things depends on what I do to the other parameter. Do I let that other parameter vary? Do I hold that other parameter constant? And so forth. So what we've done is we've taken different trajectories through a design space. And by taking different trajectories through a design space, we tend to draw conclusions that look like they're contradictory. Yes?
Does that mean you didn't necessarily define all the design space if you...
What?
Doesn't that mean you didn't necessarily define all the design space if some of the variables you didn't really choose?
That's a good way to look at it. I was very careful to define the design space, but I was silent on how I was handling the other degrees of freedom in the design space when I only looked at one variable. I was very careful to define what the design space was, but I chose to.
So you don't have to.
What?
You don't have to choose what you get to define.
That's right. We know what the design space is, and to really understand what goes on, we need to look at what we do with both variables in a two-dimensional design space, not just one. Now, if I'd already fabricated this circuit, conclusion would be entirely different. Because this is at the design stage. At the design stage, the relationship between the current and the power and W over L has not been fixed. But once you fabricate the circuit, and I drop the circuit on the desk and ask the question, then the answer might be entirely different. In fact, if I fabricated the circuit, W over L has to be fixed. I could still change the quiescent current. I could let that current source come out. So the relationship that I would have would be this quadratic relationship, because W over L is fixed. Make sense? At the design stage, W over L is not fixed. But once the circuit is designed, W and L are fixed in that silicon, and it can no longer change. Now, I intentionally looked at this relatively simple circuit because it's easy to demonstrate what happens when you don't consider your whole design space. Do you think this problem goes away if you have a circuit that has more degrees of freedom in your design?
No.
Not at all. It becomes more difficult for me to explain what's going on, but it's still there. Make sense? The choice of design parameters can have a major impact on insight in the design. We saw that at the end of the period last time and the beginning of the period this time. For this particular circuit, P and Vx's bias seem to work very well for the design parameters to work with. The size of the parameter domain should agree with the number of degrees of freedom of the circuit. We spent quite a bit of time talking about the number of design parameters we have and the number of degrees of freedom. You have a choice of either doing that or ignoring it. But if you ignore it, it's still there. So if you're going to do a good job of design, you probably don't want to ignore it. You might as well want to know what it really is. The effects of any parameter on performance, whether it be in the identified parameter domain, natural or practical or small signal parameter domain, the effects of any parameter on the performance is not strongly dependent. That's not word right. Another mistake in that mistake list. The effects of any parameter on performance is strongly dependent upon how the design space is explored. The small signal and natural parameter domains typically give little insight into design or performance. Even though we use the small signal parameter domain to analyze a circuit, we typically don't find that a useful domain for designing a circuit. So now let's try to tie the close the loop in regard to what we talked about in 330. This op amp that we now talked about, this circuit is often known as the common source amplifier. Oftentimes we don't think about using a feedback configuration, but it works fine in a feedback configuration. The gain is in the 30 to 45 dB range. Not a fantastically high gain. It's high enough that in some applications it will still give reasonable performance as a feedback amplifier. This is inherently a transconductance amplifier since the output impedance is high. Input impedance is high and output impedance is high. So it's really a transconductance amplifier. The voltage gain is the ratio of the transconductance gain to the output conductance. Well, that's true in any structure because you can put in the two-port model and the voltage gain will be the ratio of GM to GM. It's critical to know the degrees of freedom of the design and how to systematically explore the design space. How many people have problem 3 done? Where you're asked to analyze a circuit and spend no more than half an hour doing it. How many people have that done?
I've heard that's the one to skip.
Yeah. The reason I had the homework assignments due Wednesday, of course, was I didn't expect you to start until Tuesday of next week on it. What you're going to find is that the analysis of some of these circuits can be quite tedious, and that's why there was a half an hour constraint on solving that problem by hand, even though it's a relatively simple circuit. So another reason we looked at the circuit in detail is we're going to, by inspection, write down the performance of differential circuits based upon understanding the performance of single circuits. Okay. Here's another view of what happens when you explore the design space for this amplifier. So I'm looking at now the gain bandwidth product as one of the parameters of interest as a function of the excess bias and the power. And you can see that if you explore this along a line here, this would be along constant excess bias lines. We might have a linear relationship because these linear lines. If I do it under constant power, we've got a different line. But I could go at an angle. I could explore the design space going diagonally like this. Make sense? So you can explore that design space along many different trajectories and you get what appear to be different results as you explored along different trajectories. Examples we looked at were just exploring this over 2 or 3 different trajectories through this plane. So let's look at differential input structures right now. As I stated earlier, the differential input op-amps can be readily obtained from single-input op-amps. We'll show how to do that. And the performance characteristics of the differential op-amps can be directly obtained from those of the single-input counterparts. Analytical expressions for even simple op-amps can become very complicated if brute force analysis techniques are used. On problem 3, you'll find you only have to write 3 equations. Pretty easy to write 3 equations. Solving those 3 equations is a different story. Considerable insight into both performance and design can be obtained from a systematic strategy for design and analysis of op-amps. If you've got a very complicated design strategy, you won't get much insight in regard to how that circuit's going to perform. Most authors present operational amplifiers from an appear and analyze approach. We talked about this in lecture 1. We're going to see how we approach it from a synthesis approach rather than an appear and analyze approach. So here's a theorem. If a linear network is symmetric, then for all differential symmetric excitations, the small signal voltage is 0 at all points on the axis of symmetry. That's a mouthful. If a linear network is symmetric, then all differential symmetric excitations, then for all differential symmetric excitations, the small signal voltage is 0 at all points on the axis of symmetry. Can we prove that?
I had a question then about homework 3, or question 3, so then would you technically just solve for half of the circuit, and then that would simplify it?
That would simplify it a lot. However, in problem 3, I didn't assume that the left side and the right side were matched.
Okay. Yeah, because the current here is connected kind of like a diode.
Yes.
And so it would be different from this side.
Well, in the left and the right transistors, I didn't initially assume they were matched.
Oh, okay.
I don't believe. We will eventually assume they're matched, but right now, I left them unmatched.
Oh.
And then, consequently, this theorem will apply. But the useful application of that circuit is when they're matched. Okay? So, what we do is we build a circuit and just rotate the circuit around the axis of symmetry. What we mean, so that gives our symmetric circuit. And we said we're excited, small signal excitation, this differential. So that means if this voltage goes up, this one goes down, and vice versa. And then we can take any point along here, the small signal voltage here is 0. Can we prove that? So linear circuits, so superposition applies, right? Linear circuits, so superposition applies. So let me take a point here, and I'm going to look at the transfer function from here to here. And I can say that this voltage here is equal to, if I excite it here, is equal to transfer function times the differential input. So some voltage on the axis of symmetry, VZ, is equal to V1, voltage on the left, times the transfer function T1Z, plus the voltage V2 times T2Z. So Z is a point on the axis symmetry. I have two transfer functions, transfer function from here to here, and a transfer function from here to here. Right? If it's symmetric, how does T1Z relate to T2Z? They're the same. But T1Z and T2Z are the same, so I'm just going to call that TZ. So VZ is equal to T of Z times V1 plus V2. But what was my assumption about V1 and V2?
V2 equals minus V1.
V2 is equal to minus V1. So if V2 is equal to minus V1, then this is 0. So V of Z, 0. Okay. That's pretty impressive. There could be a lot of nodes on that axis symmetry. Any transfer function with differential excitation is going to be 0 to that node. Here, symmetric outputs of a symmetric network excited differentially have no common mode components if biased on the axis symmetry with an ideal current source. So I have a symmetric network. I'm biasing it on the axis symmetry with a current source. And I'm saying the common mode components are 0. Common mode components are 0. So what do I mean by common mode component? So let's assume I put inputs in here, a common mode input. So instead of having VD and minus VD, I have the same voltage on both sides. And what would happen if I take a circuit here, bias with a current source, and have these voltages go up together or down together? What?
Wouldn't you get, you said if they were equal versus equal opposite.
Yeah, they're equal. Well, let them be equal now, because that's the common mode input now. Common mode input means I put the common signals in both sides, not differential signals.
VZ equals 2
Yeah, it wouldn't be two.
VT VDT Z.
If they have a common mode component, if these voltages go up and down, oh, I said that. I didn't make a mistake, but I want to look at the differential excitation first. So here, if I excite it differentially, no matter what the current is, the average value of this voltage won't be changing. And so there is no common mode component if we bias it on the tail with a current source.
Should the common modes component cancel out in a differential setting?
Should what?
Should the common mode component cancel out in a differential setting? It seems like that's what the theorem is implying.
You can look at it as the combo component canceling out, or it's not there. So here's what's happening. Maybe so let's assume that I've got VDD up here. And maybe I have a couple of resistors here or something else. And here's V out minus and here's V out plus. And I've got a current source here biasing it. And I've got inputs right here. If I put a common mode signal in here, this current is still going to split equally between the left and the right side. So this current here and this current here will be the same, and they'll be half of this current. So even if I excite this network with a common mode signal, this current on both sides won't change. If the current on both sides won't change, I get no change in the quiescent output. And hence, there is no common mode component associated with the excitations. Is that clear? If these voltages go up and down, common mode excitation, and this current is fixed on the axis symmetry, that means these currents are going to be fixed. If these currents are fixed, these voltages can't change. So that's what this theorem says. Let me define something called a counterpart network. The counterpart network of a network is obtained by replacing all N-channel devices with P-channel devices, replacing all P-channel devices with N-channel devices, replacing VSS biases with VDD biases, and replacing all VDD biases with VSS biases. So I'm defining a certain network now. So here's an example. This is a network that has some N-channel devices. And I'm going to replace VSS with VDD. I'm going to somehow have this VDD on top there. Mistake number 3. I'm going to replace the N-channel device with P-channel devices. So I replace M1 with M3. I replace N2 with N4. I keep the same connections for the structure. So this becomes the counterpart network to this one. Here's the simple common source transistor, single transistor. Replace VDD with VSS. Replace the N channel with the P channel. So this is a counterpart network. So I can give you any network, and if you just blatantly substitute P's for N's, blatantly replace VDDs with VSS's, you obtain the counterpart network. Yes?
What's the usefulness of this? Why would we want to do that then?
If I can't show it's useful, we will remove it in the future. So I've got 2 theorems too. You should have asked me why those theorems are being given. Are they useful? Is it useful to just say, oh, that's kind of a cute theorem? So my goal is to be able to synthesize networks. So if I know some properties about symmetric networks and differential networks, I'm going to be able to synthesize networks that have certain properties. Okay? This definition of a counterpart network, other people have probably used the concept. I don't think the terminology is the same. The counterpart of a network is unique. If A is the counterpart of B, then B is the counterpart of A. The counterpart of the counterpart is the original network. So the counterpart of this is this. The counterpart of this goes back to this. Theorem. The parametric expressions for all small signal characteristics, such as voltage gain, output impedance, and transconductance of a network, and the counterpart network are the same. So, if you go back to this network here, the small signal voltage gain from here to here is going to be GM over G out. Small signal gain voltage gain from here to here is GM over G out. It's true for any network and its counterpart. Small signal expressions are the same. Values aren't the same because the parameters of the devices may be different, but the expressions are the same. Now, this is something we can now talk about after we've talked about the definition of a network as counterpart network and symmetry. So this is now synthesis of fully differential op-amps from symmetric networks and counterpart networks. Theorem. If F is any network with a single input and P is its counterpart network, then the following circuits are fully differential op-amps. Okay, so what have I done here? I take any network F, I create its counterpart network, and I put them together and create what's called a half circuit. And then I reflect them around an axis of symmetry. And I define the output between the network and its counterpart network. I bias it with VDD and VSS. I put an input on the original network, on the left side and the right side. And I pull a differential op-amp. And there's another structure that has the same property. Instead of biasing this is called the tail down here. Here we're biasing it in the tail with voltage source VSS. We're biasing on the axis of symmetry. Here we're biasing on the axis of symmetry with a current source. Or we're biasing the tail with a current source. So these are fully differential op-amps. So that means if I take any circuit, I can immediately convert that circuit into a fully differential op-amp. So that's the synthesis strategy, right? Start with some circuit and synthesize a fully differential op-amp. In fact, this op-amp, does it have differential output or singulated output? It's all in the eyes of the beholder. The circuit has differential output, but I could ignore one of them, and they would have singulated output, right? So this structure has differential inputs and differential outputs. Or singulated outputs if I ignore one. So the question is, what do we do with the extra output? And the idea was, we could ignore it or use it. So, I'm gonna refer to this original network as a quarter circuit. And I take the quarter circuit and its counterpart circuit and put them together, and I form a half circle. And then I take the symmetric version of the half circuit to form the whole fully differential op amp. So now what do we really start with? We just really start with one circuit, the quarter circuit. From that quarter circuit, we get the fully differential op amp. I think we're out of time. So let me make one observation, and then we'll be done. Further, most of the properties of the operational amplifier can be obtained by inspection from those of the quarter circuit. So when you look at that fully differential op amp, there may be a lot of components in that fully differential op amp. And the analysis of that fully differential op amp may be very tedious. This suggests that if I understand how that quarter circuit works, I can write down by inspection the characteristics of the fully differential op amp. Does that make sense? Are there any questions? I hope we've answered your question why we talked about the counterpart circuit, why we've talked about symmetric circuits, why we talked about axisymmetry, because we put all these together to be able to build or synthesize our op amps. That's all today, thanks.
Oh, yeah, for sure. I mean, like, I hardly use it now. I don't get I've watched design books before. It's very, I think I'll probably, you know, so design oh my God. Oh,
Actually, they both do exactly the same thing, so we've got some mistakes there.
So, right, because you're not, if I do format, lambda is 0.25 micro.
So the lambda is early voltage.
But I don't want to sell
Oh.
We were using the regular lambda. Lambda means feature size, or lambda means 1 over V.
Then it would cancel that, but it makes units. Okay. All right.
Yep. So, Professor, for this problem, this is our ideal current source, right? Because my VGS, VB2 is also constant.
Yep.
This will draw all the stuff.
Yep, that's correct. So we're biasing this on the tail with the current source.
And this is symmetrical.
Single room on campus.
Sources are linked to VB and VGS.
So he's not quite symmetric. Since we made this connection here, we're not biasing this out.
But I mean, it's biased to symmetries.
That's right.
Wouldn't it be the way to write all of these things since the gate gives it's probably the
So the question is this drain voltage the same as this drain voltage?
Yeah.
No?
No.
If I increase or decrease the inputs, I'm going to put more or less current on the side. So that voltage will go up and down.
How do you approach this? Do I just analyze?
How do you like the reading?
So what do you
How do you like the reading?
It was actually pretty interesting.
I definitely like this one Wednesdays.
Oh yeah, I agree with that.
Does the current split?
There was some like spill over to like
you have to say things correctly. I feel like Paul walks through there and then you gotta say things correctly.
Like, can you imagine if somebody made some little screw up, you'd have to redo the whole thing?
Imagine like it's 12 years old.
What happens if it's some newbie and he just keeps fucking up?
It's like, I'm wondering if you'll do it during class.
That's right.
Sorry, you said it wrong and I have to go over again.
See if you'll-
It would be amusing.
So for here, here, and here.
I can't imagine he'd do it more than once though, because I feel like some of us would get so flustered that we wouldn't be able to not do it.
It's a mixture of people getting annoyed at
Wow, we were both hoping to get our
Embarrassed.
movie 35.
The anxiety level.
Is that possible?
Certainly. You've got my office, I can get you.
Okay, cool. Is that something we